Hamiltonian, therefore the derivative with respect to time is equal to 0, and the Poisson commute between themselves, which means that I pick up any two of them, then the Poisson bracket is equal to 0, then the system is integrable in Newville sense, meaning that you can basically find explicit solution up to some finite number of integration, and this should be, in principle, be possible, even if the explicit solution most of the time is not achievable. Of course, there are several examples for this integrable model, and the easiest one you can think of is the harmonic chain. So it's not even the harmonic chain, it's something simpler. You have a lot of particles moving independently. So your Hamiltonian H1 will be the sum of pj squared over 2 plus qj squared over 2. Pj are called the momenta usually. The qj's are the position of the particle. Then and you have your standard Poisson bracket, which is between f and g that you can see here on screen. Then it's easy to see that the function aj1, which is pj squared over 2 plus qj squared over 2, is a constant of motion for the system, meaning that the derivative with respect to time is equal to 0. And there are n of those. They are independent. They are in involution. Therefore, the system is integrable. In this case, you can actually write down explicitly the solution of the model. I just want to point out that you can see probably the aj1. If you sum all of them over j, then you get back the Hamiltonian H1. And this property is something we are going to leverage quite a lot because it's something that is really general, meaning that it's really easy to find out that several integral motion are actually sum of some local conserved quantities, which are these aj1. They don't have to be strictly conserved, the aj1, but they sum has to be conserved. This is how we call local conserved fields. And this is going to play a really big role in the derivation that we're going to see later on. Finding this integral motion, h1 up to hn, is a really difficult task because, I mean, nobody keeps you how to do it, but there are at least two ways of finding them in a constructive way. One is the Lax pair, they're going to see in a minute, and the other one is to find a Hamiltonian structure, B-Poisson structure. In particular, what does it mean to find a Lax pair for a model? It means that I have my equation of motion in thermodynamics, so xj dot equal to a Poisson bracket between xj and the Hamiltonian. Then I can rewrite them as a linear system of D for a matrices L and A, and I want the derivative with respect to time of L to be equal to the commutator between L and A. And this is called a Poisson bracket. Why this structure is so important? Well, because in this way we have for free, by the property of the commutator, then both the eigenvalues and the traces of L to the power k are constant of motion for the model. They are independent and in involution. Those two are, you see, there are n, in principle, there are n different eigenvalues and n different traces at very least, if your matrix is n times n, for example. But they are not independent, okay, between the two sets. So I can consider just one set as independent conserved quantities or the other. So we are not having a system which is called superintegral when you have actually two n conserved quantities. There are big differences between the eigenvalues and the traces. In particular, as you can probably imagine, the eigenvalues are non-local, meaning that they depend on the structure of all my system. Instead, the traces of L to the power k, they have some chance to be local because, for example, if the matrix is just a diagonal, then these traces can be written as the sum of local quantities, meaning that they just depend on a finite number of particles, and this is going to be like fundamental. We are going to play a bit with both of these conserved quantities, so keep them in mind. What I want to do, I want to study statistical property of this model, so I have to decide a measure. I have to pick up the initial data according to some measure, and the most natural one is the Gibbs measure. How this Gibbs measure is structured? Well, you have a first term, which is an invariant measure for the dynamics, and this can be the Lebesgue measure or any other particular measure for the model. And what does it mean that this is invariant? It means that the density mu tilde x is derivative with respect to time is equal to 0. Then I can attach this exponential term in terms of the trace of some potential of my lax matrices L. And why I do this? Because if I think about V to be just a polynomial potential, for example, well, those traces are going to be conserved. And this in particular implies that my measure mu of x is going to be invariant for the dynamics. So I have a really broad family of invariant measures that I can pick from. And none of them is actually really, I mean, better than the other for dynamical property, just that some of them is going to be possible to push some computation for some other is not. And for the sake of the talk, we're going to actually speak about potential V, who are going to be just polynomials. What I want to do with this mu x, I'm thinking to sample initial data according to this measure, and then I want to study statistical quantities for the long time behavior. And here there is already a little glimpse of connection between the theory of integrable system and random matrix theory, which is one of the probabilistic tools that I'm going to leverage in order to obtain my result. And in particular, if you have this measure mu x, you sample initial data, then the entries of L are going to be sampled according to this measure mu of x, and this makes the matrices L to be random. And now you can ask whatever question you want about this matrix. So what's the eigenvalue distribution? If there exists a central limit theorem for the density of states or the eigenvalue distribution, what's the behavior of the biggest eigenvalues? So we have a lot of setting of tools coming from random matrix theory. They can help us maybe say something about the statistical behavior of my model. What I want to study specifically are the correlation function for this system, which are like, as you can see here on screen. And specifically, I want to compute them when time is large. Why I want to do that? Because for a short time, you have a lot of weird effect of dissipation, and like maybe there's some things that are really weird that I cannot track. So I have hope to obtain large T limit. And one of the reasons why also I want to use this is that there is a general tool in the theory of integrable models, which is called the Riemann-Hilbert problem, that deals with long time asymptotics. So any result that we have analytically track on this integrable model is actually for long time. Okay, so the best result that we can get is for a long time. That's why one want to guess this at first. Moreover, this large time behavior of the correlation function is related to transport property of the system, specifically their conductivity. Along the talk and in general, there is a lot of effort in studying one-dimensional integrable models because they are the ones that we study the best. And these integrable models have a really specific behavior, which is called anomalous transport, which means that their transport coefficient of the chain of this particle increases in n. And this looks like a really mathematical feature, but it can actually be explicitly measured with experiment. And this is a picture that I took from a paper in Nature. So they put this chain of, I don't remember the chemical name, but this chain of particles between two conductors and makes electricity flows. They compute experimentally the transport coefficient, and they see that it increases as the length of the chain increases up to some point where the chain fall apart because of other physical restriction. So it's something that actually you can see, and it's something then worth studying.
So sorry, Guido, so capital N is the...
Yes, so sorry, capital N is the number of particles in the chain.
Okay, and in the previous slide, when you show that covariance, when you subtract expectation xj, there is no t because there
is not time dependent, that quantity. Xj of t or xj of 0, they are exactly the same because the measure is invariant. Okay, so I can compute that one at any time. Instead, the first term is time, depends on time because I cannot shift back in time because the t will get back into x1 of minus t then.
Thanks.
Okay, no, thank you. I mean, this makes everything way more clear. Okay, now I have to go through all of these, sorry. Okay, so what's a bit the state of the art on computation of this correlation function for several models? So we have I would say the big result in 2011 from Spohn and Lukarinen when they proved that in dimension bigger than 3, then this correlation function are exponentially decaying. And this is a mathematically rigorous result, but they cannot access a low dimension because of some dimension restriction, exactly. But the advantage of low dimensional model is that they can be actually studied numerically pretty well. And from the early 2000 up to now, there have been several numerical investigation of this model, meaning that you can actually compute numerically the correlation function. And what they notice is that this correlation behave like this. So you have a damping term in front, 1 over t to the gamma, and this function f evaluated at j minus vt, which means that the center is going to move with some velocity v, and there is and the center. Sorry, you have to think of f as a function which has a bump at 0. So this evaluation at j minus vt means that this bump is going to move from to the right or to the left depending on the velocity, and lambda t to the delta is gonna make it being narrow and narrow. So you're gonna see like two peaks moving and then shrinking over time. But it's not just that. There are basically 3, we'll say, universality class for this kind of behavior. There is the one of a non-integrable model where gamma and delta are the same, is equal to 2/3, and f is related to the solution of the KPZ fixed point. For nonlinear integrable system, gamma and delta should be equal to 1, and the function is just the exponential. And then there is the linear integrable models, which are the short-range harmonic chain and the short-range harmonic chain that are there is a full description for them, and one can actually study the correlation function really, really deeply, like obtaining basically any regime results. Since I'm hardwired with this kind of definition, for nonlinear integrable system, this behavior of that gamma and delta are equal to 1 is called ballistic behavior. Okay, so if I say ballistic behavior, then you can understand that it is the behavior of the correlation function that I'm referring to. Recently, it was when I started my PhD. Now is more than 5 years probably. The theory of generalized hydrodynamics gets in play, probably even older than that. And what's the aim of this theory is to study these models, which I mean both integrable and non-integrable system, under a wider perspective, meaning that they want to get some hydrodynamic equation that describe effectively the model. And through this hydrodynamic description, one should be able to compute the correlation function, or at least give a good approximation to them. This theory went on for a while, and actually, at least one of the early computation of the correlation function from start to finish using generalized hydrodynamics that I know of is the one of Spohn, that he was able to compute the correlation function for the Toda lattice. And after that, they will consider several spin chain model where people were able to compute their correlation. And this theory was pushed to quantum integrable system, specifically by Doyon and his crew. And there is also a kind of twin to this theory of generalized dynamics for integrable PDE, which is called Soyton gas theory. And over there, even in this theory, the aim is to find some sort of hydrodynamic description of the model that describes the behavior of the system per se. I want to stress that most part of this theory still needs a mathematical foundation, meaning that there is a lot of I would say physical black box, meaning that there are some approximation, there are some really deep physical intuition that makes things work, but mathematically speaking, one needs to work hard on this. And recently there was a paper, there's 2 papers by Amol Agrawal that worked a bit on the Toda lattice, like trying to study some sort of behavior, not of a correlation function, but the long-time asymptotics for this system that will enable one to compute a correlation function more rigorously, mathematically speaking, and they are like pretty heavy mathematically, I would say. I'm still digesting them a little bit, but I think it's important to point them out. But my final point is that this theory, something has to be correct, because on the right-hand side, you see this dotted line. Those are the generalized dynamic prediction of the correlation function for the Toda lattice obtained by Spohn. And then all the correlate lines, so the green, red, and blue, are the correlation function that I numerically computed on the high-performance computing here in Tulane. And as you can see, they match perfectly, okay? So despite needing a mathematical foundation, they matches like perfectly. And it was a bit annoyed by this, honestly speaking, because I was hoping to find some I don't know, some mismatch, but it's not. So probably what we have to do as mathematical community, try to actually prove that what the physicists are doing is in the end correct. The central point of the analysis for this generalized dynamics is the so-called density of states of the system. So let's make a bit of recap and go through the definition. First off, we have my Hamiltonian equation. So xj dot is equal to the Poisson bracket between xj and h. These equations of motion are equivalent to the Lax equation, L dot equal to the commutator between L and A. And this means that my eigenvalue lambda j are conserved. So the eigenvalue of L are conserved. But now I'm considering the case where the entries of the matrices L are distributed according to some measure, mu of x, which is my Gibbs measure, which means that the eigenvalues are conserved and random. Okay, so it makes sense to ask what's the distribution in the Largian limit, and this is exactly the density of state. So I'm seeking for measure the sigma lambda such that the limit that you see on screen holds true for any function f continuous and bounded. Computing this is not trivial, since, for example, Toda and also all the other models, the Volterra and other integrable system, their eigenvalue distribution and their distribution on the entries are not the usual one that are studied in random matrix theory. Meaning, in random matrix theory, probably you know there is this Gaussian beta-ensemble or this family of beta-ensembles. Well, the distribution that we are dealing here are definitely different, and I will show you with an example later on in what I mean by that. Now, given the density of states, what's the general recipe to find the correlation function for your favorite integrable model? So first off, we start with our constant quantity, constant quantity hk. And these are going to consider them as a sum from j up to n of some local conserved field at j of k. One that is going to be there all the time is, for example, the sum of the momenta. So the total momentum of a system is conserved, but each single pj is not conserved. Okay, so this is the pj are going to be my local conserved quantities, and the sum of them is my conserved quantity, okay? And there are n of those, okay? So there are n different conserved quantity, and all of them can be written in this form. Now, for each local conserved quantity, I know that I can write this evolution as a difference between two functions, j of j plus 1 minus j of j, which are called local currents, okay? So why are called currents? Because they basically describe how the energy passed through the chain. Since my conserved quantity hk is all conserved, but each little piece is not, and this piece is local, the evolution of my local conserved quantity is a good indicator of the flux between a range of particles and the one nearby them. And that's why these conserved quantities, the local conserved field, are important to compute the conductivity of the model. And last but not least, I need to define what is called the total current, which is just the sum of my local current. So if I do this, the second step is to be able to compute the expected value of this quantity in terms of my density of states, which here are called sigma. And these L1, L2, L3, L4 are, in general, they should be some operator. And we will see that in the case that we know the solution, these are actually just integral operator. I want to stress out that I have to take the expected value of AJK, and this one is I would say, the easy one. And then the first line is kind of given. But for all the other three, you need to work case by case. Okay, there is not a general theory that tells you, oh, well, now L2 is going to look like this, L3 is going to look like this, S4 is going to look like this. So it's really case-based. And even if there is a general belief that one should be able to push the calculation more or less the same way for all the known integrable model, well, this is still definitely not a theorem. You have these 4 expression in terms of the density of states, then, well, the second step is actually to write down some hydrodynamic equation for the model, which are going to be more or less all the same based on L1, L2, L3, and 4. But for these things, there is a recipe to do it. And again, it's not mathematically rigorous, but is I would say, physical derivation, which means that is definitely makes sense mathematically wise, but there are some steps that one has to clear at very least. And when you do that, well, you can compute the correlation function. That's basically, I know we say automatic, but the third step is like you have to actually show that you can solve a system of differential equation. And maybe it's hard, maybe it's easy, but that's definitely you can do, and you can obtain the behavior of this correlation function. Okay. So I would say that step 2 and 3 are the one that still mathematically need to add some rigor. Step 1 instead is case-based, but is mathematically rigorous up until now. Okay. How do I compute this functional, and how do I compute my density of states? Because these are the 2 main characters of all my derivation. I want to use some tool coming from random matrix theory, and you might know that in random matrix theory, one tool used to actually characterize the density of states is this called large deviation principle. So you want to prove that your measure sigma can be characterized as the minimizer of some functional, and then it's characterized. So this minimizer is unique, so you know how to deal with your sigma. You can get an expression maybe for it using some technology coming from running the problem. But when you have something like this, you're happy. But how to prove that this large divisor principle exists, and how to find explicitly what's this function, which is the phi of sigma, which is called the rate function of the model? Well, one idea is to try to use what we already know. So we are mathematicians, so we will never invent anything new if we can use already something else that is already known. And this is exactly the driven force right now, is say, well, random matrix model, classical β-ensemble, I know a lot of them. Let's try to use them in order to find my density of states for my integrable model. And this was exactly what led Herbert Spohn to obtain this first computation of the correlation function. And what he did is he picked up the Toda lattice, and he proved that it was deeply related to the so-called β-ensemble, Gaussian β-ensemble at high temperature. The Gaussian β-ensemble is the most classic, I would say, Gaussian beta-ensemble studied. This matrix representation was introduced by Dimitri and Edelman, but the introduction of the Gaussian beta-ensemble, the Gaussian ensemble, actually goes back to Wishart, so the beginning of the study of random matrix model to study nuclear physics. The label high temperature for the expert means that my parameter beta of the beta ensemble actually scales with n as 2 alpha over n. and why it's called high temperature, because beta can be interpreted as the beta can be interpreted as the temperature of the system, so as the inverse of the temperature of the system. So as n goes to infinity, beta goes to 0, which means the temperature gets high. After Herbert obtained this relation between these two models, well, me and other author pushed this to other integrable system and other classical beta-ensembles, as you can see on the table. And for people who knows, on the left-hand side, you basically have all your the classical random matrix ensemble that we all know and love. And on the right-hand side, we have some of the integrable system. Still, there's still work to do to actually make a perfect matching between left and right. Here and now, we're going to just focus on the last line, the anti-symmetric Gaussian beta-ensemble, and the Volterra Lattice. So we're going to go a little bit deep into this relation. So what's the Volterra Lattice? The Volterra Lattice is this integrable system. It was thought to study the population evolution of some system. It was solved by Kakenweinberg using the inverse scattering transform, and is also proved that it is a discrete approximation of the KdV equation. And for all these reasons, I think it is worth a study, meaning that the KdV is one of the stereotypical integrable PDE that everybody wants to study, and the models nonlinear waves. So probably the Volterra Lattice is a good analog of it in the discrete setting. Since it's an integrable model, I told you about Lax pair before. The Hamiltonian equation of motion of this system, it can be rephrased in this form as a Lax pair between the matrix L and A, and L is on screen and is a anti-symmetric periodic matrices. And as a refresh, I know that the traces of L to power k are constant of motion for the system. It's for free. This is for free from the Lax equation. And now the last bit of information I need to give you for the setting on the Volterra side is the generalized Gibbs ensemble that I'm going to use. So the density of the distribution on the entries of L at time equal to 0. So I have my matrices, I have my traces are constant of motion, then I can define my Gibbs measure like this. This key distribution is just for the indicator function of aj bigger than 0. And this V you can actually think of as just a polynomial of degree 2n, which is -1 to the n plus 1 for because otherwise the measure mu will not be normalizable. Okay, so if you think of V in this setting, this is any measure that works, and one can try to work out any correlation function within any of those. But the numerics that I'm going to show you, and also to just keep everything on a bit on the more on the ground, the Gibbs measure that I'm gonna actually consider is just this simple one when V was just now the x squared, so the quadratic potential. Okay. And now it's time to try to apply the receipt. So we have my constant of motion, which are the traces of L to the power 2k of L to the 2k. And up to this -1 to the k, I can rewrite them as sum of the entries on the diagonal. Why I want to do this? Because now these one are local conserved fields. So in view of the structure of the matrices, each entries is going to depend just on a finite number of particles independent of n, up to the fact that n has to be sufficiently big. I can just rewrite those in terms of some fixed number of particles that depends on k. Then I can rewrite my my local currents using the Lax matrix, the Lax equation form, and then I have my local currents. Okay, so the first step is done, and now how do I go and push this to the functional relation? Well, in view of the fact that these constant quantities are just these local conserved fields are just the JJ entries of my matrices to the power 2k, then is easy to see that one can rewrite them as the kth moment of my density of states, And this is, again, this is basically for free using just the definition of the density of states of the model. The hard part, and that's why with this energetic wave, the expected value of the currents is the hard one. So you have to tweak a bit around, do some mathematical trick to be able to express it in terms of the density of states, the sigma, in this form, when qk is just the kth moment of my density of states, and this v effective is some explicit function that is given in terms, again, of sigma. Okay, so now you have these two. You can compute also the two correlations between the moments and the local currents. So you are good to go. The only thing that's left, sorry, to be able to compute is my density of states, d sigma, and then one should be able to apply all the receipt. How you do that? Well, you have to go through these anti-symmetric Gaussian β-ensemble, which are the β-ensemble which represented matrices is this anti-symmetric Q. You don't see any periodicity here because that's the standard way of presenting it, but there is it's easy to see that if they're just rank one perturbation, nothing will actually change. And this is the density of state, the entries distribution of this anti-symmetric Gaussian β-ensemble, which was introduced, sorry, I didn't say that, by Dumitriu and Forrester. And again, to keep things a bit easier, you have just to think of, if you pick up your potential to be just x squared, then this is the measure that you are gonna put inside the in the entries, and all of those are gonna, then each yj is gonna be independent of each other. Why I want to put this measure, this particular measure, on these matrices? Well, because then I can express, I can explicitly compute the Jacobian transformation from the matrices to the eigenvalues, and the first entries of the first row of the orthogonalizing matrices, and then I can write down this eigenvalue distribution explicitly. So the eigenvalues of those matrices are going to be explicitly distributed in this way. And this is also a kind of nice physical interpretation, because again, you can see this van der Monde term, these product terms. If you put in the exponent, then it's going to have this log potential, which is exactly the Coulomb potential. And then you can think as your V, the potential that you put on the matrices, as external fields, which every particles is subject to, and all these particles are interacting in this way. So these also have some physical application. And again, you can now start to see why this now is beta tilde, is called the temperature of the model, because it's related exactly to the interaction. So if you see this as an Hamiltonian system, then B tilde would be exactly my temperature. Now, what I want to do, I want to push to the high temperature regime. Why? Because in this way, I don't know if you noticed before, the what I see here. So the yj's, the exponent of yj's were depending on n, and they were growing in n. Instead, in my previous definition on the Volterra lattice, these exponents were not depending on n. So to avoid this, at least to make it bounded, I want to go to the high temperature regime, where this beta tilde now is going to be beta over n. And the price that I have to pay is that now the density, the eigenvalue distribution is going to be slightly different, and also the distribution of the entries of the matrices. Okay, perfect. Why this is important? Because now I can actually characterize the density of states of this model in terms of some large deviation principle, which means that my Gaussian anti-symmetric β-ensemble, the density of states can be explicitly computed and can be explicitly characterized as a minimizer of this functional. And I want to tell you, usually for general potential V, you cannot explicitly compute the density, but there are numerical methods that allow you to do so with really high precision. And when V is particularly simple, for example, some polynomial or some monomial, then you can actually compute this density of states using Riemann-Hilbert technology. But what I want now is that, okay, I have this density of the Gaussian symmetric β-ensemble. How do I push this information to obtain the density of states of the Volterra lattice? Well, now the relation between the two models comes a bit more explicitly if you look it up at the distribution on the entries of each two matrices. Remember, Q and L are really close to each other. They are both anti-symmetric, and the only difference is that one is periodic, the other is not. So it's just a rank one perturbation, one of the other. And the other huge difference is that in one case is the exponent of yj depends on the position of the particle j by this term j over 2n. Instead, for my Volterra lattice model, these aj are all distributed in the same way. This relation, and playing a bit around with the matrix representation and with some moment matching technique, allows us to say that the density of states of the Volterra lattice, sigma of x, is just equal to the derivative with respect to beta of beta times the density of states of the anti-symmetric β-ensemble. And I want to stress that this is something that works all the time. So it's a really, really general result that I obtained with Ronan Memin, where that you have two matrices. They are they are basically the same, except they are one a rank one perturbation of the other. If the entries of one are distributed in the stairway, so you have these stairs, and in the other one, you have this line, so all the entries are distributed in the same way, well, then this relation between the two density of states is gonna hold, okay? We proved that just for polynomial potential. I think that one can actually push it a bit farther than that, but for V polynomial that works, and this is what physicists are actually interested in. So, okay, all of this to tell you, well, now I have my density of states, and I have my completed my second step in the receipt to obtain the correlation function of the model. So I have all of this relation, and now what I have to do, I call my favorite physicist, which for me is Rick, of course, and he applying a general technique. He's gonna give me the linear approximation of my correlation function. So this was really the hard part, the mathematical rigorous part. Then it becomes a bit more physically driven, all the derivation. But a bit more seriously, what actually they claim to do is that you have all this relation on the right-hand side of the board, then you can rewrite your equation of motion for your local conserved fields averaged, and when you put them together, then you obtain a hydrodynamic equation for your model in this form, where this k is related to the first moment of the density of states. You have these two hydrodynamic equation, and using this hydrodynamic approximation, you can actually compute the correlation function of the system. And after a bit of work, this is what you get for the approximation for the correlation function of the Volterra lattice in the large n limit. And also k is explicitly given, which is related to the first moment of the density of state sigma, which is again given. This is a delta function evaluated at some point where Vf and Q are known. And this one dressing and this psi of V to the power m are two explicit function. This m should be 1, actually, sorry, here, are two explicitly given function in terms, again, of the density of states. So everything is explicit and also can be numerically computed. So it's something that is actually, you can obtain this correlation numerically. But I want to point out something, that this delta is gonna hit 0 at some point. So for some value of x and t, I'm gonna hit 0. Well, this sigma of the density of states, when evaluated at 0, it goes to infinity, it blows up, which means that the correlation function can be discontinuous, which is something that doesn't make any sense. Because on the left side, we started with something with smooth, and on the right-hand side, we have something which is not smooth. How does it work, and why this is true? This is exactly what I wonder. I wonder that I made mistakes probably in the derivation for like a month, and then I decide, okay, let's do some numerics, and this is what the numerics show. The dotted line are the generalized dynamic prediction of the correlation function for the Volterra lattice, and the side zero is the space-time point where the x over t is 0. So this is the point when I have a discontinuity. Well, in the point of discontinuity, the numerics show a higher order effect. So a higher order waves, they smooth out the discontinuity, which is like way, way bigger. So this is an effect that one can say, okay, it's a secondary effect. It doesn't really matter. It's something that you can see. I mean, it's actually the biggest thing is in the picture, okay? But this is not captured by this linear approximation of the model. To be fair and square, Benjamin Donjon, I was not aware of that while I was working on this project, but then my reviewer pointed out, well, there is also this work. Can you actually try to apply that equation of generalized dynamic to the system? Because he came out with an equation that should also include the dissipative terms, but like the program of finding explicitly the values that you need to obtain to actually make that like workable, so that you can actually carry out all the calculation analytically and obtain some guessing for the generalized dynamic correlation function. This is something which is not feasible, at least at this moment, but it might be that with this second order approximation, they can be able to actually track also this oscillation, but it's something that it should be done, definitely. And the second one is just to show you that actually this is not that I picked up specific value for beta such that this happens. It happens for all the time. So for any values of beta, you're going to have something like this. And I want to stress that it's believed that I'm considering always a periodic system. I didn't stress it out a lot. And indeed, you can see that on the right-hand side, the blue line is going a bit higher. And this is for boundary effect. But we always consider it when the period n goes to infinity, so it's get bigger and bigger and bigger. So these boundary effects, you should not be seeing them. But again, just want to point it out. Thank you so much for having me. And if you have questions, I'm here to answer.
Thank you very much, Guido. So let's see if we have questions or comments.
So I have a question. So you mentioned these experiments about the conductivity, that the conductivity grows with n, and so from this for the Volterra lattice, what is the prediction of the growth with n of the conductivity?
It should be like oh my goodness, because the correlation decay like 1 over t, so it should be the log of n.
Okay.
Should increase like the logarithm of n.
And in these experiments that you mentioned, do they have some prediction for the growth, or is it's too short?
I don't know. I don't know. I don't remember it. I think they do have some like they have some. I think they have some graph about like the theoretical prediction and what actually is what they see, but I'm not sure. I'm not completely sure. I think I remember seeing graph of theoretical prediction and what's actually happening there. But this is not Volterra anyway. This is something else. This is I think something way more complicated that they are trying to tackle.
Okay, thank you.
Any more questions? Guido, sorry, in the Volterra example, you didn't show us the matrix A, so it didn't play any role in the recipe?
Yeah, it does a little bit when you want to compute the evolution of the local constant quantity, that you need the matrices A. But
okay.
rather than that, you really don't need it. It's something that you can. I mean, it's not worth it to show you also that part of information, I think, in doing a talk.
Thanks. So if there are no more questions, let's thank Guido again.
Thank you.
Thank you very much, and we update next Wednesday. Bye bye. Ciao, ciao.
Ciao.